Okay, the third topic that I'm going to talk about is the covariance, which is about how to quantify the degree of dependence between the two random variables. So the goal of this part is to make a metric of dependence degree between the two random variables. So given two random variables x and y, we'd like to assign some number that quantifies the degree of their dependence. The example of quantifying the degree of dependence is that the feeling like happy or sad versus the weather, they may have some dependence, but our question is the strength of their dependence. Sometimes to some people they can be weak, or to some people they can be strong. Okay? How can we quantify this? Another example is the university ranking versus annual salary. It may have some correlation, but again, how strong they are dependent on each other. So what we need to do is to make a metric, design a metric, and then there will be some requirements that we can think of before we design a metric. First, obviously the metric should increase as they are more dependent, or respectively decrease as they become less dependent, right? And we hope that if they are independent, this metric's value should be 0. So that's our first requirement. And the second requirement is that, well, dependence may have some direction, right? For example, if they are positively dependent, meaning that whenever the x goes up, then the y also goes up. Or the other way around, that's a negative dependence direction. And somehow our metric, we hope that, is able to show this direction of the dependence, for example, using the plus and minus. Third requirement is that since we're talking about the dependence between the two random variables, and the random variables sometimes can represent some time, can represent anything that we're interested in, right? Which means that the random variables may have some dimension. That also means that the range of the random variables can be very diverse, sometimes between the 10 and 1000, sometimes like minus 2000 to the 100 and so on, okay? But obviously when we make a metric, we would like to have this metric have some kind of bounded numbers, for example, like minus 1 and 1. Otherwise, we have a very situation dependent numbers, which can be sometimes very big or sometimes very small. Okay, so that would not be very appropriate for a good metric. We would like to have the scenario where our metric is always bounded by some numbers like minus 1 and plus 1. So that's a third requirement. You know, the good engineers, so there are many features that the good engineers should have, and I believe that the good engineers should be good at making good metrics. For example, suppose that somebody tells you to make a metric of how our society is economically polarized. Then what kind of metric are you going to use in order to assess this thing? Okay? If you know what's happening in the Major League Baseball, for example, then there are lots of cyber metrics they are using. When you go to the MLB homepage, then you can see this kind of a lot of metrics. There are many metrics, but they are using this kind of all kinds of the metrics to evaluate the quality of the team and the players. So that's what we are talking about in this section. All right, so then let's become good engineers. Okay. All right, how can we design the metric that quantifies the degree of dependence? All right, in order to simplify the situation, let's assume the situation where expectation of the two random variables are 0. Okay. Now we're going to recover this thing into a more general case. What do you mean by the dependent? Well, that means that whenever x goes up, then a y tend to have large values. That's a sort of positive dependence. And the other way around, whenever the x goes up, but the y tend to have small values, then that's a negative dependence. Okay. So that's a dependent. If you are given this homework, then what kind of things are you going to use to quantify this thing, this dependence? Somebody can propose, okay, what about the expectation of x multiplied by y? So if you think about this thing, like expectation of xy for a moment, it seems not bad. Because again, whenever x goes up, then y also goes up, then the expectation of xy will be very large. But the other way around, then it will be very small. Okay? And also, when the x and y's are independent, we know that the expectation of xy is equal to the expectation of x multiplied by the expectation of y. That is equal to 0. So that also satisfies the first requirement. So for example, suppose that we have a lot of data when the xy is positive. Well, it's possible that both of the data are positive. That's why we have xy is positive. Or it's possible that the both are negative. So we have xy is positive, which is okay, right? So whenever x goes down, then the y also tend to have a small values. Then the expectation should be large. I mean the metric should have the large values, and an expectation of xy also satisfies that thing. The other way around, x goes up, but the y goes down, then this expectation of xy may have small values. Okay, so for the negative dependence, we have minus values. For the positive dependence, we have a plus values. And also they are independent, then what? The 0. Okay? Note that the expectation of xy, the absolute value of expectation xy, also quantifies the amount of the spread, right? Which means that even if the xy have a positive dependence, then it may have this kind of pattern. Data can be this pattern, or sometimes data can have that pattern. These two patterns are different. Even if these two patterns shows the positive dependence, for the red case, we have a small amount of the spread, but whereas in the blue case, we have large amount of the spread. So expectation of xy also includes the information about how much spread data have. Okay. Somebody asked the question, okay, what about the expectation of x plus y? Is this a good metric for our purpose or not? Well, the answer is, well, it's not that good, because when they are positively dependent, but what happens if they negative values? I'm talking about this case. And then this expectation may have negative values. Okay, but what we want to have is that, okay, for all kind of positive dependence, we want that some metric has a positive values. We like this expectation of xy. All right. Now the question is, what happens if the expectation is not 0? All right, then somehow we need to modify the expectation of xy just a little bit, but still the properties that we want to have are sustained. Okay, how can we do that? Do we have an idea? Yes, we have an idea, and the answer is the centering. Okay, centering is always useful. Okay, so what we can do is that we want to define another random variable x that is a centered version of x, like x minus mu x and y minus mu x. Then obviously the expectation of x minus mu x is 0. So we can recover the original like simpler cases, and then we can sort of maintain the important properties of the metric that we want to develop. Okay. So finally, we're going to define some notion which we call covariance. And the covariance x comma y is nothing but an expectation of the centered version of two random variables. That is x minus expectation of x multiply the y minus expectation of y. Okay, so far we're happy about this metric in order to quantify the degree of dependence. And after some algebra, you can see that this covariance of x comma y is expectation of xy minus expectation of x multiplied by expectation of y. So how can we show that? This is equal to the expectation xy Okay. Is equal to. So here in this case, this expectation becomes now constant, right? So this expectation, and also this becomes constant, and this is constant. Oh, sorry, this should be plus. Okay, so it's gone. So we get this. All right. This as a kind of another definition of the covariance from now on. Right. Now, as we have mentioned, if x and y's are independent, then the covariance x, y is 0. You know why? Because if the x and y's are independent, this multiplication of expectation of xy is equal to the expectation x and expectation y, so they should be equal. All right. You may ask the question that okay, what happens if the covariance is 0? Then the x and y's are independent? The answer is no. So when the covariance xy is in 0, then we have a different terminology because it does not directly imply the independence, and we call they are uncorrelated. Okay, so that means again independence implies uncorrelated, but uncorrelated does not imply independence. So let me give you an example where the covariance of xy is 0 but not independent. Okay, so here the situation, we have 4 data points of x and y, 1, 0, 0, 1, and minus 1, 0, and the 0, minus 1 with all same probability 1/4. That's the joint PMF of x, y. Then you can easily check that the covariance x, y is 0. That's because the expectation of x is 0 and expectation y is 0. We can compute this expectation here. First, compute the marginal distribution of x, and then you can compute this. So by computing this one, this expectation, before having this formal derivation, everything is symmetric between the -1 and 1 and so on, right? In terms of x-axis and in terms of y-axis. So the expectation should be 0. And expectation xy also becomes 0 because all the multiplication of these meaningful 4 points, they have a 0 values. This guy and this guy expectation is 0, so that's why covariance, and that is 0. Okay, but they are independent? Well, obviously no, because for example, somebody gives it information that the x is equal to 1, then we should have the y is equal to 0, because I have only 1 point with a positive probability. Otherwise it's 0 when the x is equal to 1. So we should have the y is equal to. So x and y's are very dependent. It's not independent. Okay. There are some properties that we need to check. First, what happens to the covariance x, x? And that is equal to this thing, right? And that is equal to the variance of x. And the reason why this is true, that if you remember, the covariance metric also measures the amount of the spread as well as the degree of the dependence. So if we do the computation of the covariance between the x and x, it only captures the amount of the spread. That's why this becomes variance. All right. Second property is the covariance ax plus b, y is by definition this. Then it becomes like a expectation of xy plus b expectation of y minus a expectation of x and expectation of y plus b expectation y. So minus. So this is cancelled. So a expectation xy minus a expectation x multiplied by expectation y. A multiplied by the covariance xy. Okay. So here, as you can see, this b, which is again the additive term, does not make an impact on the covariance. But here, multiplicative term will make an impact. Now, what happens to the distributed law? Well, distributed law is satisfied, meaning the covariance x, y plus z is equal to the covariance x comma y plus covariance x comma z. Okay, and that is because of this definition. Variance of x plus y, by definition, that is equal to the expectation of x plus y square and minus square expectation of x plus y. Then we already checked that in I don't know, maybe previous lectures. Previous lectures. That's the variance x plus variance y plus 2 covariance x plus y. And you can check that this is equal to x plus. That is equal to the here. Okay. So you can match here and here and here and here. That's the variance x plus variance y. And 2 expectation of xy minus 2 expectation x multiplied by expectation y. So that's why we have 2 covariance xy. Generally, we can extend to the variance of the summation of, for example, like 1 to n, then the summation of each guy's variance plus all the cases of the I is not equal to j, the covariance xij. And this is a general form of this guy. All right. Do you remember that we have covered the hat problem in lecture 3? Yeah, the n people throw their hat in a box and then they pick one at random, and then we have computed the expectation and the variance and so on. So we're gonna again compute the variance using the covariance formula of the previous slides. Here the x is a number of people with their own hats, if you remember. We're interested in a variance of x. And in computing this thing, there were 2 key steps. First is we define a random variable xi is equal to 1, which is the Bernoulli random variable if I selects own hat and 0 otherwise. And that's why the x is a summation of xi of all people. And the key step is 2 is that, well, the xi's are independent. The answer was no. Okay, because for example, like depending on the first guy pick his own head or not, the second guy's result depends on that. Okay, so xi is a Bernoulli random variable with the 1 over n parameter 1 over n, because it's the same as the making a sequence of the selecting the head. So the first guy, the distribution of the xi is equal to the x1 because of the symmetry of the problem. So the success probability of the picking its own head is 1 over n, and the expectation is the probability of xi is equal to 1, such that 1 over n. And the variance of each xi is just 1 over n multiplied by the 1 minus 1 over n. Okay? Yeah, that was the basic information. And what we want to compute is that we want to compute the variance of x. And using the formula of the previous slides, we have variance of each guys and the plus the covariance of all cases of I is not equal to j. So let's use that formula. So if the I is not equal to j, let's first compute the covariance xij. All right, and this is definition of the covariance, and that is equal to the probability xi is 1 and xij is 1, and minus, we know that this is 1 over n, so it's 1 over n squared. Right, and this is equal to the using the multiplication rule, the probability xi is equal to 1 multiplied xj is equal to 1 given the xi is equal to 1, and it turns out that this can 1 and this can 2, right? And what is the probability that the x1 is 1? That's 1 over n. And what is the probability that x2 is 1 given the x1 is 1? That's 1 over n minus 1. And 1 over n squared, and that's why we have the covariance of xij is 1 over n squared and minus 1. All right, and the variance of each guy, well, variance of each guy was 1 over n, 1 minus 1 over n, but we have n guys here, so n multiplied by the variance of each guy, and the covariance of the xi and j was this, and how many permutations that we have? That's what, np2, right? ij is not equal to each other, so that's n and minus 1. Okay, so we have, it's gone and it's gone, so that's why the variance is 1.